Thank you. So I'm Anthony Fox. I'm from Virginia and a company called CCRI, and I'm talking today about extracting location intelligence from data using GeoMesa on Spark SQL. Thank you for attending this session. So first things first, the kind of data that I'm talking about is the kind of data that companies like exactEarth collect. exactEarth is a company that flies a constellation of satellites, and you can actually see the satellite pattern in this particular visualization. They collect AIS data. AIS is the automated identification system that all marine vessels are broadcasting their location and identifying information to neighbors, nearby vessels, to relay stations for the purposes of safety and navigation. We had maritime, now we've got air, and this is the kind of data that's collected by companies like FlightAware. FlightAware collects ADS-B, which is the Automated Dependent Surveillance Broadcast. The FAA mandates that all airplanes have an ADS-B transponder where they broadcast their position information and their identifying information to nearby airplanes, to relay stations, to air traffic control centers, and to anybody with an ADS-B receiver. And you can buy these receivers, you can build these receivers. It's a lot of data. I want to pause for a second and talk about this particular visualization, which is the type of ad hoc visualization that is very typical of users of GeoMesa. This particular query was a real-time query against a GeoMesa instance with hundreds of millions of records in it. It returned, for one query, a 36 million result data set, which it then GeoMesa encoded in Apache Arrow format and loaded the result into a standard browser, standard JavaScript. This animation is done with standard HTML5 canvas, no WebGL, no GPUs, no nothing. And some of those group bys are all powered by the Apache Arrow format. I'm going to talk in more detail about that. So we've got sea, we've got air, and we also have moving entities on the ground. And this is collected by companies like Strava. Strava is a company that has a mobile application that allows users to track their fitness activities, rides, runs, commutes, other kinds of activities. And this is a heat map produced by GeoMesa of the density of activity in downtown San Francisco. This is another heat map that is the greater metropolitan area and shows the activity that is within the Strava data set. So air, ground, and sea, lots of moving entities, lots of data being produced. In this talk, I'm going to cover what I mean by location intelligence and give a quick intro to what GeoMesa is. I'm going to talk about spatial data types, Spatial SQL. These are the things that GeoMesa has extended Spark SQL with in order to answer location intelligence questions. We're going to do a bit of a deep dive into how GeoMesa has extended the Spark Catalyst optimizer to efficiently execute spatial SQL. And we're going to go through two use cases. We're going to dissect some queries and understand how they are executed and how they get at these results quickly. So first of all, let's talk about location intelligence. To me, location intelligence is asking the following kinds of questions of your georeferenced data. And it's on a scale from easy to hard. On the easy side of things, we've got questions like, show me all the coffee shops in this neighborhood. That's really quite simple. You have a query geometry, which represents the neighborhood. It could be a bounding box or a polygon. And you have a data set that has coffee shops in it. You just use a spatial index. This is what GeoMesa does out of the box to get back data that's within that query region. Pretty simple. Next in the difficulty scale is how many users commute through this intersection every day. This is a little bit harder because you're no longer dealing with points, you have to deal with line strings. And to illustrate why, imagine you're passing through this roundabout, and the sample rate of your data stream is such that you get a ping before you enter the roundabout, then you don't get a ping until you leave the roundabout. So you have to actually aggregate that particular activity up using a line string and then do a line string intersection with the roundabout table. So a little bit more difficult, but still not very difficult. Here's a query: which users commute within 250 meters of a coffee shop? This is really any coffee shop, right? So in this case, in the first two questions, we have one spatial region for our query. In this case, we have many spatial regions. It's the location of all coffee shops. And we're joining that with our activities table. So it's a spatial join. And this is where Spark SQL really comes into play. Next up on the difficulty scale is, should I place an ad for coffee on this user's mobile device? This particular question illustrates something that's key here, which is that location intelligence questions are very low latency. In this case, we have to do a dynamic geofence, so we have to know which one of our users is near a coffee shop right now, and which one of those users is likely to purchase a cup of coffee using potentially a preference model or something to that effect. So a little bit more challenging computation and more of a real-time, low-latency question here. And the last question is, where should I build my next coffee shop? This involves an analysis, a longitudinal analysis of the change in activity and potentially a preference model for where you want to site your next business. And this is, again, this kind of batch analysis over large data sets is really where Spark SQL starts to shine. So these are just a sample of some of the questions that I think of when I think of location intelligence. So GeoMesa is a suite of tools for persisting, querying, analyzing, and streaming spatio-temporal data. It's an open source project. It's open sourced under the Eclipse Foundation's Location Tech Working Group. It's got a lot of different support for persisting data and analyzing that data in things like Cloud Bigtable and the Google Cloud Bigtable and its open source clones, Apache Accumulo and Apache HBase, as well as support for Cassandra. And you can see on the bottom row here that it also has support for a very cost-effective model of storing your location data and analyzing it in Google Cloud Storage or S3 in some of these columnar structured file formats for OLAP analytical style queries. For APIs, it exposes the standard GeoTools API, which is another open source project. This gives you a consistent API in which you can access shapefiles or PostGIS or Oracle Spatial. You can also access your data that's in Bigtable or HBase or Accumulo or Cassandra. For HTTP access, it integrates with GeoServer. This opens it up to integration with any of the mapping clients that are out there these days. So automatic integration with Leaflet, with OpenLayers, with Quantum GIS, with Google Earth, and Google Maps. And of course, Spark, which is what we're talking about here today. For analysis, the usual suspects, but I wanted to point out that something I've personally found very useful is the interactive workflow of analyzing spatial data using notebooks like Jupyter and Zeppelin. And the use cases that we're going to walk through at the end of this talk were all done using Jupyter analysis and Spark SQL on GeoMesa. And the last thing to note, that consistent API across all of those backends is also available on top of Kafka, including the HTTP Open Geospatial Consortium API, meaning that you can have data in Kafka and integrate that with Leaflet in a web map. Okay, so we talked about location intelligence, quick intro to GeoMesa. Now we're going to talk about how GeoMesa extends Spark SQL in order to get at these location intelligence questions. So anybody that's familiar with geospatial information systems, GIS, this will be very familiar to them. So GeoMesa adds the typical geometry primitives as user-defined data types to Spark. That includes points, which the exact Earth data, the flight-aware data, and the Strava data all come as, in their native form, instantaneous positions with associated metadata. It includes line strings. This is basically the moving trajectories in all three of those sample data sources rolled up into an aggregate, right? So each marine vessel voyage, an aircraft flight becomes a line string, and a user's entire activity becomes a line string. And then, of course, there's polygons. Polygons are typically used in GeoMesa on the query side of things. They're not usually the source of the high volume, high velocity data. But again, there's support for dealing with polygons and doing some of those spatial joins. The corresponding UDTs, user-defined types, are shown there, point UDT, line UDT, and polygon UDT. In addition to the spatial data types, GeoMesa adds a whole bunch of different spatial functions to Spark SQL. Here's an example of Spatial SQL. This is probably the simplest example. We're really just querying our activities table for any records that fall within a geo predicate and within a date-time range. So we've got a geometry constructor. stMakeBbox will create a geometry literal from a bounding box that we'll use as the query region. We've got a spatial column that we've added to our activities table. And we've got a topological predicate. stContains returns true when the geometry that's in the activities record is contained within the bbox that has been defined by that geometry literal. There's a whole bunch of different functions that have been added to Spark SQL. Some examples are shown here. I'll point out st_makeLine allows you to aggregate geometries up, collect them into a list, and then make a line out of them to do some of those analyses that I mentioned with respect to the roundabout. Topological predicates, there's quite a lot of these. We talked about stContains. I'll point out stDwithin is distance within. That's a radius query, so it's how many coffee shops are within 5 kilometers of my current location. And a lot of different processing functions. I'll point out here stGeohash. stGeohash will take a point geometry and encode it using a space-filling curve. Space-filling curves is how GeoMesa stores data in a structured, indexed way so that it can rapidly pull out the correct data for your query geometry. Space-filling curves is a topic I could go on for a long time about, but I chose to spare you guys of that today. But if you have any more questions, just ask me afterwards. I'll also point out stDistance spheroid. That's going to be useful to us when we go into our use cases. It computes the distance in meters between two geometries using an approximation to the Earth's shape. And one thing that I forgot to mention about stGeohash, the z-order curve and space-filling curves induce a grid on top of the region that we're analyzing. So you can start to use that to do grid-based analysis of your data, and that's going to be important when we get into our use cases. Okay, so those are the spatial data types that we've added. They're the spatial SQL functions that we've added. Now we need to talk about how we can leverage the extensibility of Spark Catalyst for optimizing that spatial SQL. Let's look again at our query. We have a number of different elements here that are candidates for optimization. And the goal that we have is to only load the partitions that have data that actually intersects with our query region. We don't want to do full table scans. Our whole goal is to not do full table scans. Spark's Catalyst Optimizer, for those of you who aren't familiar, Catalyst is responsible for taking a query, for analyzing the query and producing a logical plan, and then for optimizing that logical plan, coming up with a number of different physical plans and selecting one of those physical plans for execution. There's a bunch of different extension points within the Catalyst Optimizer. For us, the interesting extension point is in the logical optimization phase. We're going to insert some rules that will optimize queries into this phase of the processing. The Catalyst optimize, these extension points are actually marked as experimental, but the functionality was so compelling that we had to jump in with both feet. So it may change in the near future, but we'll see what happens. Okay, again, we're going to look at our query. We've got a GeoMesa relation with a spatial column. We've got a relational projection. We're only returning several of the columns, not all of the columns within our data set. We've got a topological predicate, a geometry literal, and a date range predicate. So as it stands right now, this particular query would do a full table scan, and it'll apply the ST contains predicate and the date range predicate inside of Spark SQL. We don't want to do that. We want to optimize that. So GeoMesa adds what we call the ST, the space-time contains rule, to the logical optimization phase. The space-time contains rule intersects any SQL that has a filter on a GeoMesa relation. It then inspects that filter to determine if the filter has a topological predicate or another predicate that GeoMesa can handle natively. And if it does, it rewrites the SQL abstract syntax tree into something that is more optimal. So basically, what we've done is we've gone from a syntax tree that looks like this, where we have a relational projection at the top, a filter, and the GeoMesa relation. After we pass it through the optimization phase, we remove the filter and push that down into GeoMesa so it only scans the relevant data and loads the relevant data into the RDD. And in this case, since GeoMesa actually also supports relational projection, we push that into GeoMesa as well. So we've gone from this query, which is all executed in Spark after a full table scan of GeoMesa, to this query, which is far less I/O, less network overhead, and less compute inside of GeoMesa, inside of SparkSQL. This has been very, very effective for us. Okay, so we've walked through SparkSQL and the Catalyst optimizer. We walked through some of the data sources. Now we're going to talk about a couple of use cases so that you get a feel for how to write location intelligence questions and how they get executed and how you can visualize some of the results. The first one we're going to start with is pretty simple. So this is your standard heat map query. We basically want to count up the number of records in the Strava activities table per grid cell so that we get a sense of where activity is dense, where activity is light. So this is our SQL, and we're going to dissect this. First, we're constraining to San Francisco with a topological predicate. The ST contains rule will be triggered in the processing here. Next, we snap the location to a 35-bit geohash. This is our discretizing of the space that we care about here. This is the grid that we're going to use to do analysis. We group by those geohashes and count the number of records that fall into each geohash. The result is a table with geohash and counts per geohash. At that point, we can drop down into pandas. Projected DF here is a pandas data frame, which is the result of this aggregation over a GeoMesa table. And we can visualize it using Bokeh, and that's the result, which is now GeoMesa supports native heat maps, right? So you can actually skip the whole SparkSQL step in order to do a heat map. But this really illustrates one aggregate analysis of the kind of data that we care about here. In addition to that, we can do much more complex grid-based analyses. And that's the next use case. So the next use case that I'm going to walk through is a speed profile of a metropolitan area. You may want to do a speed profile in order to understand where there are bottlenecks, and you may be able to put in dedicated bike route to reduce bottlenecks or to encourage bike commute in your metropolitan area. You may want to do a speed analysis and understand the variance or the standard deviation of speeds in a particular grid cell, because this may indicate where there's a lot of conflicting activity at various different speeds and could potentially be a safety issue. Okay, so let's dissect this query. Again, we start with a topological predicate. We're going to constrain our analysis just to just to the San Francisco area. We're going to sort by the date field so that we're getting each activity in order. And this is where we have to actually look at each record and its next record in order to derive the speed, right? So we have to use SparkSQL's window functions in order to do that. So we've sorted an activity by date time, and we can look at each record, which is a point in time, and the next record, which is the next point in time, get the difference between those points, both the distance and the speed and the time, and then derive the speed. So we use lead to get those two different points together into one row. And then we create a temporary table. The result is a table that has the start and end points and the start and end times. So now that we've got that, we can compute the distance, which is distance in meters between those 2 points. We can compute the difference in time, and we can divide the two to get meters per second for that particular record. We also, in this case, snap to a grid, and we've got now a measurement of one activity's speed in a particular grid cell. Now we create another temporary table. And you can see the result of the table. It's grid cell and speed, where grid cell is repeated a number of times here. So now we're going to group by grid cell, and we're going to compute summary statistics for each grid cell. So we compute the median using the percentile approximate function that SparkSQL provides out of the box, and the standard deviation, meters per second. And the result is a table where we have the centroid of the particular grid cell and the various statistics, which we can then repeat our analysis with pandas and bokeh and return a visualization of the speed, in this case, of activities in San Francisco. So the thing that jumped out about this to me when I was looking at it was, first, it was kind of typical. It was to be expected. There was slower speeds in the city, though there were some pockets of speed in the downtown area. But the thing that really jumped out at me was that there seemed to be high-speed Strava activity in the water, which I found kind of interesting. So I zoomed out a little bit, and it turns out that Strava users seem to turn on their app when they take flights. And they mark these flights as rides, which I guess technically they are rides. They also mark them as commutes, which maybe they are commutes. But that seems like a long time to have the app on and to be draining your battery. But, you know, it's pretty interesting. Okay, so that is the two use cases and how GeoMesa can be used with SparkSQL to do location intelligence type analyses. I hope you found that useful. Please ask any questions that you want to. I'm enthusiastic to talk about this stuff, so feel free to grab me afterwards to talk about location intelligence. Yeah. Mike.
Is this live?
My question is that now I saw these queries about querying a single fixed box contains a table with a geospatial column. But what if we have two tables, we want to do a spatial join? Do we have some optimization for that?
Yeah, so what GeoMesa will do right now is it will pick the first side and optimize the query across the first side But that's not always the right thing to do. So you kind of have to have inside knowledge of your table's cardinality. What we hope to do soon is to get a bit of cost-based optimization in there, where we can look at the cardinality of one table and compare it to the cardinality of another table and do the join appropriately.
I mean, you will do the automatic indexing for the one of the table, or is that what you are doing? I mean, if I directly write something like SD contains with a column from one table and a column from another table, will one column be indexed somewhere in the optimization?
That's a good question. I think in general, we assume that the geometry column, if you're using a GeoMesa relation, the geometry column is indexed. So both sides will be indexed, but one side might be much higher cardinality than the other side. So there is something that needs to, some optimization that needs to be done there.
Okay.
Thank you.
Thank you.
You showed the integration with SQL by UDTs and UDFs. Is there also some integration with graph engines, or graph frames, any of that? Was that planned or useful or not? You're talking about geometrical algorithms here, right? So nearest neighbor or some of those kind of typical graph problems, wouldn't they also apply here?
There is integration with a graph database. It may not be what you're thinking of. There's an Apache project called Apache RIA, which is a triple store on top of HBase-like databases, and it can index some of its spatial attributes. And it's really for RDF-like analyses. So that's worth looking into. But I don't think there's what you're getting at, which is more computational graph stuff. Yeah. Okay.
Thank you.
Sure.
Hi. It seems like when you were choosing the grid, it was a little bit of a heuristic. You had like 35-bit or something like that.
Yeah.
Is that heuristic, or is that guess sort of based upon an idealized number of activity you should have in a particular cell? Like, what sort of motivated that choice?
That was heuristic. I know that 35 bits is, I think, on the order of tens of meters, maybe. And so I wanted to get down to that length. And I knew that, but I think that's something that you would play with.
Gotcha. So it was more the actual distance than the number of people in that space.
That's right. It's not a data-derived density or grid resolution. Yeah.
So you handle the radius queries, like, within 500 feet, but do you handle time-based radius queries, like within 5 minutes, coffee shops, which you need to understand maps and traffic conditions and all of that?
There is no optimization for time radius queries, no.
Okay.
But yeah, time intervals would be a nice additional index that we've thought about off and on, but never really looked at.
Okay, so one more question here.
Sure.
So you store the data your way, or you put it like in Parquet and?
So we store it you can store it in Parquet using GeoMesa, and it'll store the spatial columns in good binary representation for effective analysis. We also store Parquet files in time-space partitioned file hierarchies, so you can do some of this partition pruning effectively.
Yeah.
And we'll also store Avro-encoded data or cryo-encoded data or arrow-encoded data inside of HBase or Bigtable, where the primary key is the space-filling curves index of the geometry. So when a query comes in, we will scan only the subset of ranges that are necessary to satisfy that query's geometry.
So, but you expect that Spark to handle the partitions, selection of the partitions, because those columns that you had in date are visible to Spark.
Yes, so Spark will execute the query that you're talking about, the time radius query. Is that what you're?
Well, the one that you push the filter down.
Yes, Spark will do the column pruning, but if you can push column pruning down into GeoMesa, you reduce your network overhead, right? So if you're only pulling out 3 or 4 columns from a 50-column schema, then you don't want to lift that out of disk, pass it across the network, and load it into Spark, where it's just going to prune it away. You want to prune it at the source.
Yeah, so what is the source here? So is the Parquet
Source is
file?
any GeoMesa relation, right? So a GeoMesa relation can reside in Bigtable, or in Accumulo, or in HBase,
Okay,
or on
so I
files.
understand that. So you're pushing down to the source.
That's
Got
right.
it.
Yep.
Okay, thank you.
Any other questions?
First, it's a very good talk, and thank you. I have a question about the UDT part. Can you talk a little bit about the Spark version you're using? Because as far as I'm aware, the UDT support for 2.x version isn't clear yet.
Yeah, so it's not public. So we actually had to put all of our UDTs in the org Apache Spark SQL namespace, package name, and then it can handle it just fine. But yeah, they don't publicize that. It's not available really externally, but we saw it and we really wanted it, so we started using it. Perhaps a little bit prematurely, but you know, it's working well for us.
Got it, thank you.
Yep.
I think we'll take the rest outside.
Okay.
You guys, a round of applause for the speaker.